All right. Well, thanks, Kristen. So this is the seventh in our webinar series that we started in probably February, March or so. And the format is that we have 15 minutes of presentations followed by 15 minutes of Q&A. And so the aim of this webinar series is mostly to facilitate collaborations and kind of exchange of ideas, basically, about initially mostly the role of salinity in the overturning circulation, but we are kind of branching out a little bit from that. So the hope is that we kind of establish some interactions and that might maybe lead to joint projects or so, proposals or papers at some point. So we're still looking for volunteers. This is probably the last one that we have scheduled for this year. So we'll probably restart in January, and then I think for February or so we got Cecile Penland on the program. But today Xiaobiao Xu is going to present, and he's going to talk about the temperature and salinity structure of the North Atlantic circulation and the associated heat and freshwater transports. Go ahead, Xiaobiao.
Thank you, Wilbur and Kristen, for having me on this. And hi, everyone. My name is Xiaobiao. I like to talk, as Wilbur just said, temperature-salinity structure of the North Atlantic circulation and the associated heat and freshwater transport. This is a result of a close collaboration between Peter at UW and Eric and me at Kier Co-op's FSU. I took the title from the paper recently published in Journal of Climate, but soon I realized that I'm not going to cover the whole thing. So really just the simplest part. And I also have a couple of slides at the very end talking a little bit on what we are working on to follow up on this. So let's go. So why we want to look more on the structure of North Atlantic circulation? After all, we know well, or at least we think we know well, the North Atlantic circulation. It is basically the basin scale AMOC, which is mostly vertical and or diapycnal, and then sub-basin scale gyres that are mostly horizontal or isopycnic. But there are quite some uncertainty regarding the partition of the meridional heat transport between these AMOC and the gyres. For example, at 25 north, we know the total heat transport is about 1.2, 1.3 petawatts. The classical decompositions, which is between vertical and horizontal, mostly say that 90% of this heat is due to AMOC, and then the remaining 10% is due to subtropical gyre. And there are many studies on that. But some people doesn't agree. For example, Talley 2003, and also more recently Ferrari and Ferreira, they say that the subtropical gyre could contribute a lot more, like 3 times or even 4 times of that. And then we know a lot less in terms of meridional freshwater transport. So are the partitions between the gyre and the AMOC on these freshwater transports. So the purpose here is to examine the circulation structure to see if we can clarify the differences in the meridional heat transport contributions. So we are going to use the result from a high-resolution regional model, which I try to convince that is really is quite realistic in many ways. One simple way or natural approach of summarizing the essential of the meridional flow of different water mass is using a so-called projecting transport on TS, which is water mass plane. For example, is shown here, which shows the northward and southward flow in red and blue across 26 north. So immediately you will be able to see that there's a overall northward flow above the density of potential density of 27.65, and then below this you have the southward NADW, and then at the very end you have the model show a little bit of northward flow of AABW. And the numbers rating, the black number right here is the transport giving within the density ranges. So these give you overall picture of the magnitude of the northward and southward flow of each water masses. And it is also useful to view the same plot from a different angle. So here we basically view from top and looking down, and the previous slide basically showed the transport on TS of this leftmost panel. Here I also show the Meridional transport evaluate in different d theta ds grid size. This will give you highlighting better the different water property of the northward and southward flow. So essentially, we can identify three circulations. The first one is the large-scale diapycnal of AMOC, so which you see overall northward flow and southward flow. And then the second one is the diapycnal component of the subtropical dry, so which you can see, although here mostly is northward, but within the layer above 27.65, you also see a certain layers you have southward flow, and that's the diapycnal component of the subtropical dry. And then finally, we have the isopycnic subtropical dry. This will be seen better in transport evaluating with the high, small d theta ds. So as you can see, the northward flow actually, if you look at in the same isopycnals, northward flow is cooler and fresher than the southward return flow. Although we don't have exactly the observational based transport on theta s plane, we do have a lot of theta s data at this latitude. Here's just one example. The red here basically show the TS diagram in the further current as well as the Antilles, east of Antilles. And then the blue ones is further east in the offshore. So basically, we expect that the flow in the further current in the western boundary is northward and the return flow is southward. And this is consistent with the view based on the model. And this is, of course, is only one latitude, and we should also look at in terms of basin scale perspectives. So to the left, of course, here we only show the vertical and the meridional, the diapycnal component. We don't have the zonal structure has been integrated. So here we see this significant difference in terms of this meridional circulation when projected in the depth and in the density. In the density, these multiple cells basically. We have the subtropical gyre and also subpolar gyre. Those are diapycnal, and then we have the overall basin scale AMOC. So the question is really, what does this difference will impact the heat and freshwater transport calculation? You know, the classical decomposition is based on Z. So one is vertical, the other is horizontal. And to answer this, of course, we need to do some calculation. So here, go back to 26 north. So to the left, I'm showing the vertical overturning. So here we have 3 lines. So the black line shows the meridional overturning stream function, and the red shows the zonal profile of temperature, the vertical profile of zonal mean temperature, and the blue line is the salinity. And these give you the vertical overturning give you 1.1 petawatts compared to 1.24, and also the freshwater, it gives you a southward freshwater transport of 0.71, and compared to a total of 0.37 southward. Both all these four numbers are very close to the best estimate based on rapid results. But looking at the diapycnal, looking at the same thing in density space. So the overturning magnitude actually is quite similar. Here you have 17, and on density you have 17.5 maybe. But the temperature profile differs quite significantly. Here on the depths, when averaged on depths, no water is warmer than 25 Celsius, while in the density coordinate, almost like more than half of about 10 store job of the northward flow has temperature warmer than 25 degrees. These result in higher, slightly higher heat transport, 1.29 compared to 1.1. But the largest difference is in salinity. In the depth coordinate, basically salinity just decreased from surface and as a function of depth. While at the density, actually a significant part of the northward flow actually has lower salinity compared to further below. And then, and this difference contributes quite significantly in terms of freshwater transport. Here, the diapycnal, for example, component give a southward freshwater transport 0.5 compared to 0.7 in density in depth coordinate. And then we can look at the gyre, the horizontal. If you look at the horizontal, so here the three panels shows the residual of the meridional flow velocity, which is pretty much the same as the original salinity, because when the zonally integrate, when evenly distributed across the basin is really small. So this essentially shows the meridional flow. And the mid panel shows the temperature anomaly or deviation from the zonal mean. So you can see the northward flow in the western boundary, you have warmer, and then return flow is cooler. In the very interesting is also in the further strait, so which I enlarge a little bit. So you have the warm bias at surface and cool bias, cool deviation, not bias, deviation at the bottom. And this warm and cold deviation cancel each other. So actually the small horizontal gyre contribution is really because of the Antilles current as well as the southward return flow. And here shows the salinity deviation. When we decompose the circulation in density space, well, the meridional flow is more or less the same, but temperature now is very different. First of all, now the whole further current is cooler than the zonal mean, and in the interior is actually opposite. So now actually the northward flow is cooler compared to the southward flow, which is consistent with the TS diagram we have seen previously. And the salinity also show fresher in the northward flow and the saltier return flow. And in terms of heat transport, now the isopycnic gyre actually transport heat southward and transport freshwater northward. But the freshwater is clearly smaller than the when evaluated on the coordinates. So if we so if we compare, if we add these horizontal, this isopycnic gyre, and in the previous slides, this diapycnal component of the subtropical gyre, then we will get like the result that subtropical gyre actually contribute about 0 perawatts of meridional heat transport, and about 0.13 storage of freshwater transport northward. The close to zero gyre heat transfer is even lower than the 10% contribution based on the classical vertical and horizontal decomposition, let alone the higher gyre contribution proposed by Talley and Ferrari. And then the northward meridional heat freshwater transport, which is also lower than the result based on vertical and horizontal decompositions, is opposite to that of the diapycnal AMOC. And this is not surprising because the gyre's freshwater transport is actually corresponding to the positive evaporation minus precipitation within the subtropical gyre, and while the AMOC contribution is corresponding to the overall negative E minus P in the northern North Atlantic that forms the North Atlantic deep water. So they have very different dynamics. So why not higher gyre heat transport? So Talley actually she calculated gyre transport. She gave a range, and this high 0.4 petawatt gyre contribution comes from using the upper part of the further current as well as Ekman transport to balance the return flow of the subtropical gyre. So here basically you have 0.56 petawatts in Ekman transport, and then 1.4 petawatts in the further current to balance this return flow, and this gives you 0.4 petawatts. But we know that in the further current, the northward flow, which I show here, the temperature salinity observed in the further current, the near surface water is warm, but also very relatively fresh, and also here you see the salty thermocline water, and then below the fresh AAIW Antarctic intermediate water. Actually, the AMOC is what contributes to the AMOC is actually the two relatively fresh component in the further current, and this is well known because the fresh water near the surface, there's no other place you have of those fresh water in the eastern side of the Atlantic basin. So they can only come from the equatorial and the South Atlantic. But we can also view this from a circulation point of view. So here I separate the basin, the full section in 3 layers. One is near surface layer, and then the thermocline water, and then the Antarctic intermediate water. So if you accumulate the volume transport from east to west to east, so you see the near surface water flow is mostly in the further current, only very slightly in the Antilles current. And then the Antarctic intermediate water is also mostly in the western boundary, and both of these components has no southward return flow. It is actually this salty thermocline water that you have a northward flow in the western boundary current, both further current and as well as the Antilles current, and then southward return flow. So actually, we can refine Talley's calculation, but using these thermocline water only to calculate the heat and freshwater transport. And we can get we get the very similar result, which is close to 0 petawatts heat transport and 0.13, actually it's 11, I think, freshwater transport. So this is consistent with the result based on diapicnyl and isopycnic decomposition. And then the second one is Ferrari and Ferreira. They get even higher, like 40% of gyre contribution. Their result is based on two numerical experiments, one with control experiment with AMOC as well as the gyre. As you can see, the overall picture is quite similar to our high-resolution simulations. Basically, you have this overall AMOC, and then a very small diapicnyl subtropical gyre, and then you have the subpolar gyre. And then this another experiment that they turn off the convection by hosing. So in this case, they turn off the AMOC. So the difference is that this control experiment, there is 0.8 petawatts northward heat transport, and this one they only have 0.3. So they conclude that the gyre can contribute near 40% of the total heat transport. But it's important to note that the two experiments, the subtropical gyre differs significantly between these two experiments. So the 0.3 petawatts represent the gyre contribution within this experiment without the AMOC, not here. Because clearly you can see the subtropical gyre here is very small. The transport is maybe within only one contour. But here is like 8.1 straw drop. So this is basically a response of the model response of turning off the AMOC. So the subtropical gyre now has to elevate the roll to transport heat northward. So we think the result that the meridional heat transport, the gyre contribution at this latitude should be really small. The subtropical gyre, however, contribute quite a bit on the freshwater transport. As I mentioned, there are more detailed work can be found in the new paper published in Journal Climate. Just a few slides on ongoing. So we have shown this meridional overturning, but then we would like to put this 2D transformation in a 3D map. So to the right, I show the upward and downward transformation across a bunch of these isopycnyls. So you can see the blue shows downward transformation, and they shows following the subtropical gyre. But then there's also both upward and downward. The downward transformation, a lot of it is due to surface forcing. So we can take out the surface forcing part, and what is left is the due to interior mixing. So we are still working on to try to understand of detail of this mixing. And thank you very much.
Great, thank you very much for that nice presentation. We're going to go to Q&A. I'm going to go ahead and unmute everyone. So just as a reminder, please don't speak up unless you raise your hand or are part of a conversation.
The conference has been unmuted.
Great. And the quick and easy way that we moderate our Q&A is just so you can raise your hand and we'll get you queued up. And if I don't introduce you, make sure you do so that we know who's speaking. And it looks like Wilbert has a question.
Thanks very much, Xiaobiao. This was a very interesting presentation, I thought. I have a question about the. I didn't really get that. You must have said it in your presentation, but about the near surface contribution. You argue that is part of the AMOC. I don't really see how that works. Can you elaborate on that a little?
Yeah. So one way, there are two ways of thinking why the surface contribution has to be part of AMOC. First, you can see from these slides. So here is the Florida current. So in the upper part, like up 100 meters or so, you have a quite fresh 36.2, or even compared to the Atlantic water. If you look at the TS diagram in the further east, you won't find any water is that fresh. So the surface water, which is relatively fresh, they have to come from South Atlantic and go through the equatorial region, which has a lot of rain and precipitation. So this is one way. The other way is you can do you can look at the circulation pattern. So you can integrate the near surface water, but actually the near surface water, the in terms of density, is mostly only takes place in the Florida Strait. In the Atlantic east of there's no such water basically.
But,
so you can
okay.
see there's no return flow.
Right. But I mean, so where does this water end up? So if I understand the
so this water will end up in the subpolar, will become part of NADW.
Okay, so I mean,
so it's not
is that consistent with the ideas of the experiments that they did with these drifters releasing it in the Gulf Stream, for instance, at shallow levels, and not one actually making it into the?
I think yes, but it's a little bit more complicated in terms of the. So, for example, you can, if we go back early, if we look at this one, so. Near the equator and the subtropics, the AMOC is very shallow because the equatorial upwelling, and but go further beyond, north of 30 degrees, the near surface water is not north. If you integrate basin-wide, it's actually not northward. It's actually most of the AMOC, if you integrate zonally, it's found in sub depths like 100 meters or even lower in the higher latitude, like around 40. So I think the drifters is probably unlikely to surface drifter is probably unlikely to capture the total meridional flow.
Okay,
Does that
great.
answer your question? Mm-hmm.
It does. Thanks, Xiaobiao.
Thanks. Paula, go ahead.
Yes, since we're on this slide, I actually don't understand why you call that cell there on the right panel at about 27.63, the one below. Yes, why do you call that subpolar gyre? That has nothing to do with the wind. If you turn the wind off, you still get that cell. That actually, I think, is a diffusively, everybody, I think, usually thinks that that's a diffusively, diapically diffusive cell, and has not much to do with the wind-driven circulation in the subpolar gyre. In fact, I think the signature of the wind-driven subpolar gyre cell you can see a little bit in the left side panel at the very top, that a blue cell centered at about 45, 50 degrees north and very shallow up. If you think about how the Ekman transport goes in the subpolar gyre, you're still in the region of Wesley's. So you should have southward flow at the surface and northward flow at returning the Ekman transport, which is opposite to what you've indicated as subpolar gyre. So I'm just questioning the nomenclature here of calling that the that cell due to the subpolar gyre. I think that is incorrect. It is in the subpolar region, but it's not wind-driven. You can
Well,
see.
I didn't specifically say it's wind-driven. I mean, even the subtropical gyre, the overturning component cannot be wind-driven, right?
Yes,
you have
can.
to have.
You have the Ekman transport, right, going in one direction, southward, and it has to be returned at depth.
No, but on density space, you have to have transformation.
Sure, agreed. So you do have to have that. Yes, yeah. No doubt about that. Otherwise, you would have nothing. Yes, agreed.
Mm-hmm.
But that, and there are transformations that are enabled by the wind-driven circulation. I don't think that this is direct. The one that you call subpolar gyre is directly enabled by the.
It's Labrador seawater, and it's overturning circulation from convective overturning.
Yeah, I would
Yes,
say.
but it doesn't. Yes, but I wouldn't say it's. Yes, but it's not
It's
directly wind-driven.
It's in the subpolar latitudes, but I
Yes.
agree. The gyres probably isn't the best word, but
Yeah. I think the way I say subpolar gyre is probably confusing, because mostly we are talking about the dipycnal component. But
Yeah.
I guess what I'm trying to say is these dipycnal transformation in the so I guess it's associated with the subpolar circulation to me.
It's in the subpolar region, no doubt about that.
But I think one of the nice contrasts here in the right-hand panel is that it really identifies these less than global scale overturning cells, which the basin scale overturning cells, subtropical mode water, 18-degree water on the one hand, and Labrador Sea water and related Erminger Sea convective waters in the subpolar gyre, and that these are not always distinguished in the AMOC discussion. And when we talk about AMOC versus gyres, we really want to specify the sort of global AMOC, pole-to-pole AMOC versus the basin scale subgyres.
Yeah. Got it.
Thank you.
Okay, we still have a number of questions. I saw that Zoli had his hand up. Go ahead.
Yes, hello. Very nice presentation, Xiaobiao. I've been talking about some of these questions with Peter Rines a bit, and I guess I have one comment and I have one question, kind of relating to Wilbert's and Towler's questions. I guess the one comment is that I am aware of drifter studies that find that no floats deployed south of 40 degrees or so make it into the subpolar gyre, and these are floats that are drilled at 15 meters. So I still don't understand the mismatch between drifter studies and your results for the surface water, because 15 meters should be in the surface next layer. They should be being pushed where the wind is going. So if they're not making it to the north, I don't understand what's going on. But I'm wondering if part of the reason why there is this mismatch, if that's related to the fact that you were doing all of your calculations in density space, whereas if you're looking at the surface layer, that density space is inappropriate because of seasonality. And so to give some numbers, I've looked carefully in the Florida Straits, and there's a very strong seasonal cycle in temperature in the upper 100 meters. It has a magnitude of about 4 degrees centigrade over the course of the year. And the average temperature, or I guess the de-season temperature at the surface, is about 25 degrees. So the temperature you were showing in your in density space going up to 29, that to me looks like you're not accounting for seasonality. And so I'm wondering if the seasonal effects of surface warming in the subtropics and in the subpolar gyre could account for these mismatches that people are trying to understand.
Okay. Well, actually, I do calculate seasonally. Actually, because density space, density also changes. So those dash lines, actually, those are in the seasonal temperature. So you said the Florida current temperature could be as cold as 25 degree in the winter?
So if I remove the seasonal cycle in the Florida Straits, these are using observations. I fit an annual harmonic. The surface water is 25 degrees at the warmest, and that seasonal cycle covers the upper 100 meters. And then below that, I think the density space analysis is more appropriate.
Okay. Thank you. Mm-hmm.
Further north, I guess, is my hand up? My hand is up.
Go for it.
Serpa Hakkinen and I have written some papers about the transition from subtropical to subpolar gyre, and Susan Lozier has written some with her colleagues. And I think we agree really strongly that the transfer of water from subtropics to subpolar is quite deep, and we saw it down to 600 or 800 meters of the warming signal that's moved into the far northern Atlantic over the since 1996 to the mid 2000s. That's a deep signal, and the drifters, surface drifters, are clearly not showing it as strongly. I disagree with the statement that no drifters ever penetrate from subtropics to further north, because we've seen that some of them do, but it is relatively few. And Susan Lozier has a nice story of the complex way in which the subsurface flow can make that transition. We also do. It's not yet published. It's it's unpublished in numerous NSF proposals that unfortunately were not funded. But the transition zone between the Gulf Stream and the North Atlantic Current is a key place of water mass transformation, and that's involved in connecting these two regions. And it's very strongly subsurface.
So Peter, is what you're saying is going on then? Is that the surface water gets mixed down, and that's how it?
Yeah.
From the Gulf Stream to the North Atlantic Current, and that's how it gets north?
Yeah, and it's a very intricate long story, and there were some wonderful contributions from like the modeling study of I think Desbrières et al. and Mercier in France, which argued that the decline of the subpolar gyre transport, the round and round wind-driven transport of the subpolar gyre for many, many years that was evident in altimetry, has changed the plumbing between the subtropics and the subpolar gyre by shrinking the subpolar gyre back and changing the entrainment between northern and subtropical waters in that transition zone. So it's some wonderful detailed studies, and I think those of us who are interested in the details have trouble communicating this to the AMOC crowd, really, because so much of AMOC is zonally averaged and loses all this detail. We don't even see in the YZ overturning, we don't see the sub-basin scale overturning gyres. So we have a communication problem.
Thanks, Peter.
Great. Mike, do you have a question?
Yes. So you talked about overturning in horizontal gyres. There's a third gyre that often isn't pulled out from the other two, which is purely baroclinic. Did you look at the importance of that? So it has 0 horizontal average and 0 vertical average.
No, I totally didn't look at it.
Okay. Because the work I did with Bob Pickart in the Labrador Sea, we found that the horizontal gyre was, I think, 70% of the heat transport. The overturning was 5%, and this baroclinic gyre was 20 or so percent. So it wasn't negligible. I know that's at a different latitude and things are different there, but
okay.
I would think you could do a similar thing with your data.
And you mentioned Labrador Sea. Which paper are you referring to?
It's Pickard and Spall. I don't remember what year it is. Late 2000s. Okay. 2007 maybe.
Okay. I will try to follow up a little bit because I was because in this part we didn't look at the Labrador Sea. We look at subpolar, but mostly the eastern section rather than.
No,
Labrador
that's fine.
Sea.
I'm not.
No, we want to look
at
it
in particular. Just that in that application, the baroclinic gyre was important.
Okay. But I guess probably here will be a little bit different, right? I mean.
Oh yeah, probably.
Yeah.
I mean, certainly the relative influence of the horizontal and overturning are completely different in the subtropical gyre than they are in
That's right. Because the Labrador Sea you have mostly barotropic flow basically. So when you integrate, you have a little bit residual. But here is pretty much the baroclinic flow, I guess.
I think Mike's models with a really three-dimensional picture of these different overturning and transfer modes is really insightful. And the more we get away from zonal averaging, I think the better in a sense. And with 18-degree water, climb mode, subtropical mode water, if you average zonally, you can miss a lot of the pitnal activity of kind of like a Walker cell, the zonal overturning rather than the radial overturning cell. And so the more three-dimensional we get, and I think the more we get onto the theta S plane, which encompasses both volume, heat, and freshwater transport in one diagram, the better.
Great. Are there any more questions?